Hi, my name is John Leung. I'm a principal engineer at Intel. I'm also on one of the offices in the DMTF as VP of Alliances. So I create alliances with other standard bodies. So the standards body of SNIA, OFA, NVMe. I've helped DMTF establish all those in addition to OCP. I'm also a member of the steering committee at OCP, which is the Open Compute Program project, and I'm the representative to the hardware management project. So I've established Redfish as the required manageability interface within OCP. Okay? So what I like to do is talk about implementations of Redfish and the extension to Swordfish in some cases. Unfortunately, I will have no bubble diagrams in this presentation at all, so I hope you've had enough of those. And I want to thank you, SNIA, for putting me second, because I have a presentation at 11:30 at the Intel campus in Santa Clara, so I will be leaving immediately after this presentation. Okay, first thing is DMTF. So DMTF develops standards which exposes manageability, namely Redfish. But DMTF has a very, very strict policy of being implementation neutral. It does not want to show any favoritism toward any particular implementation, and it does that so it can encourage innovation below the interface, whether that be implemented in hardware or implemented in software. The DMTF really takes a very strict policy against that. In one case, the OpenBMC actually wanted to have an alliance partnership with us, and we said, we can't. If we let you, we have an alliance partnership with you, we have one with every implementation of Redfish. So even though Redfish has this policy, the other alliance partners within the DMTF doesn't. So SNIA can advocate its own. Other standard bodies can advocate their own. So Redfish implementations exist in firmware in the BMC. That's a baseboard management controller, a small little thing, service with trickle power. Most people know about that. But it's also hosted, implemented as software agents. So in a number of cases, people have said, well, I haven't got a microcontroller. Where do I run Redfish? You can actually run on top of the OS itself. And so when we originally implemented, designed Redfish, there were a number of people who came from IPMI. So IPMI runs on the BMC. And they said, in order to do this transition from IPI to Redfish, you cannot specify a standard which requires more compute power or more memory. Because what we'd like to do is be able to take the firmware that we drop in a BMC today, which supports IPMI, replace it with another piece of firmware that runs Redfish. And we can't do that if Redfish says, oh, and then we'll do this. You need to wait for another hardware cycle to implement a larger BMC on your hardware or actually put more memory on your BMC. So there was a very tight constraint on the definition of Redfish initially to make sure that it would be plug compatible firmware-wise with the BMC. That's all dealt with in the first line. So OpenBMC is actually a software implementation, a firmware implementation of Redfish, which runs on a BMC. That constraint was the same constraint that we had to fit within a BMC. As BMCs grow, they could grow, but they could grow no faster. Now, there's another part of the organization which says, I don't run in this out-of-band interface architecture with a BMC. I run on top of the OS. I got lots of memory. I got lots of compute power. Why are you constraining me? So yes, I can take BMC, OpenBMC, and run it on top of the OS, but it's still constrained. It pretends it's in a system without a whole lot of memory and a whole lot of compute power. So several implementations. I've listed it here, one in Python, The newest one I found was one in Java, C++ implementation, and a golang implementation, which has been ongoing for about a year and a half. So I'll go through each one of these. You notice there's a column which tells you what language it is, so you can pick your own poison as to what you want to implement. So as you go out to vendors and you ask them to implement Swordfish and why they haven't implemented Swordfish, and they'll tell you, it take a while for us to do this implementation. You can point them to the open source implementations that will give them a head start in actually getting this implementation now. On the far right is actually who owns it. So these are owned by various organizations. OpenBMB is owned by Leung's Foundation. SNIA owns the Swordfish emulator. And Pygmy, which does industrial IoT implementations, is implemented in Java. And OCP, which I said I represent, has two implementations in this. The last column is auto-generating. So as Rochelle did her presentation, there were lots of resources. So lots of definitions of lots of objects. So there are implementations where you actually code everything. You get a new resource, you have to go start implementing that resource from scratch. And then there is the concept of auto-generation. Since Redfish is defined, so it defines a schema which describes the object. And that schema is defined in three formats. It's defined in OData, it's defined in JSON schema, it's defined in OpenAPI, also known as Swagger. And that defines the entire additional resource. So there's a concept of auto-generation where you can just auto-generate this code. There's no particular reason why you have to code it from scratch other than you want to be a nice developer. You can actually go take the schema and auto-generate it. And that's one of the reasons we actually implemented an OpenAPI schema, because the OpenAPI guy said, from Calco said, we have the standard where we can just take the schema and start generating OpenAPI code to connect into our toolchain. And so Redfish implemented an OpenAPI interface. In JSON schema, it was obvious based on the fact that it was JSON. Okay, so at least two of these, the Swordfish emulator has a generator which actually auto-generates Python code, and the Redfish service framework, which is in Java, has a generator which will auto-generate Java code to connect into the framework. So let's go talk about the Redfish service emulator, which I know most of because it actually derives itself from the Redfish emulator. And we designed the Redfish emulator very early in the early days. It was Redfish came out in 2015. The emulator came out in 2016. And it was, we knew Redfish was going to expand beyond servers, and it was going to new management domains. And those management domains would cause new interfaces and new interactions across the interface. And instead of waiting for all this code to get generated and dumped into a BMC, we wanted to create an emulator which basically said, you want to create new objects? You can create new objects. You want them to behave in a certain way, you can code up a behavior that you want, and now you can go test the client against that interface. And as you decide that that interface quite isn't behaving the way you want, you can recode your resource, and you can make it behave somewhere else, and then eventually you will get to the type of interaction that you want to go do with that. That's exactly what happened with NVMe, is that they were defining a whole new interface with a whole bunch of new resources, and they want to know exactly what that interaction would be. So Rochelle drove a plan to take the Redfish emulator and extend it to do the Swordfish emulator. One thing about the Redfish emulator was it was designed for multiple instantiations. So it wasn't a matter of you can instantiate one Redfish service. It was built to run on a cloud boundary. So you could build a Redfish service, and you could instantiate as many copies as you want in a Foundry, and they would all have unique IP addresses, so they would be addressable. So if you want to go define a rack manager or data center manager which manage multiple instantiations of Redfish, you could do that. The instantiations would all be on some cloud, but you could now code up your orchestrator to go do that. And so on the right-hand side is basically you could start it on your own laptop, and then when you got comfortable with it, you could launch multiple copies within the Foundry. It also had a first emulator. We had simulators and whatever. They did HTTP gets, nothing else. We extended that to do HTTP patches, and then HTTP pushes and posts, so you could actually create additional objects within the interface. And then we started to auto-generate, but the auto-generation was purely for mockups. You do a simple mockup, you can now go generate code in Python. So what the way Rochelle designed this was, and she actually put more time than I did in the actual original emulator, was to now she can implement, dynamically emulate all schema objects within the entire framework of Swordfish. So all the bubble diagrams and all the resources you see, she can auto-generate all that code and connect it up to her Swordfish emulator. In addition to that, she handled most of the baseline services. So events, tasks, all the requirements that you need, she can now implement. And actually, it now passes the SNIA conformance test. You can run the SNIA conformance test, which she mentioned, against the emulator, and it would all pass. Because, again, if there's a bug, you go fix the emulator to go emulate it correctly. And what this also allowed us to do early on was that before a lot of Redfish implementations were there, people could go and start writing Redfish clients because you had something to go test against. That would be clean, and you didn't have to wait to buy additional equipment. You didn't have to buy anything. You just have to go launch this thing against a Cloud Foundry. So OpenBMC. So this is the only slide that we have on OpenBMC. The reason is because there's so much been written on it. It's been around for 6-7 years now. All I can tell you is that when Intel decided it wanted to add a Redfish interface to an OpenC implementation, it found 6 repositories owned by very large companies, all different versions of OpenBMC. And so it took 6 to 9 months to rally all those together and say, guys, we got to have one repository, and when we decide what that repository is, then Intel will implement a Redfish interface on top of that. So we finally were able to accomplish that. They all agreed that, hey, we should contribute all this to the Linux Foundation. That's a nice independent party to own all this stuff. And so once it was in the Intel layered a Redfish interface on top of that. Again, I mentioned it runs only on a BMC, so that's a small microcontroller. General features, and I just pulled this directly off the wiki. There's far more information on the repository. So it's based on Yocto. So various firmware vendors can actually modify the build script and integrate the particular driver into it. And it's also used for general distribution. It uses a dbus interconnect to do a software interconnect between other components. And it included a web interface, which is called Web UI. So I talked to you a little about the Redfish emulator. So it was in 2016 when it was released. In 2018, I think Rochelle began the extension of it, and to this day, it's still being extended. So most of the models for Swordfish are there. It was used to prototype managing for NVMe over fiber channel and NVMe over Ethernet. In 2021, which was, 2 years ago, it became the base of what Open Fabric Alliance uses for their Open Fabric management framework. So OFA had the concept of, fabrics are a lot alike. Redfish models fabrics a lot alike. And so therefore, there should be an opportunity here to do a single implementation to manage any fabric, whether it be XL, whether it be SCSI, whether it be any type of fabric or PCIe, anything. So that they embarked upon that in 2021, and they started with this implementation of the Swordfish simulator. So the thing, which in 2016 had the concept of you just stub everything out and it would execute, now became something where the stubs are now removed, and we actually start touching real hardware directly. And so that's what the Open Fabric Management Framework's concept is, that it actually create a framework where you can, instead of doing stubs, you do actual plugins, so you can manage various types of networks. And that's still ongoing. And so the latest is the NVMe Swordfish service. So this is now using Python, using plugins to manage NVMe devices. And Red Hat took a look at it and said, this is nice, pretty good. What are you going to do with this? And they said, well, we're going to keep it at open source. He goes, well, can we just drop it in Red Hat release and as a Red Hat plugin? And we said, sure. So I think sometime this year, later this year, it will either be incorporated as into Red Hat, or it will be a addition you can plug in at Red Hat. So now you have a software agent that you can just drop on top of Linux that you can go implement, okay? So this has had a long history of starting with one capability and one goal and ending up with a wholly different goal. So this is just a framework of what the Open Fabric Management Framework looks like. The only thing that I will mention is that the management layers have Redfish coming in and Redfish going out. So this is managing devices that actually support Redfish. But the top layer is to manage the overall fabric. So the ones on the right hand side are all the plugins for all the types of fabrics you could have, whether they be OmniPath, Slingshot, InfiniBand, CXL, which is basically proves out the model that they were trying to go implement. And this is the detail on the Redfish service for CXL. And so this, as I mentioned, they're still in the process of making this public. They actually added now a persistent database, because the way the emulator is written, of course, you fire up the emulator, it creates everything from scratch, and once you kill the emulator, everything disappears. Okay, the second implementation is in Java, and this has actually been released in the last week. As I mentioned, as an alliance partner rep, I create alliance partners with various other organizations. So PicMig approached us and said, we do a bunch of Pigment cards, VME cards, I think is the history. We want to go into something different. We want to do industrial IoT. And we want to go use the Redfish model to go do this. And we said, go. We want Redfish to be used in many management domains as necessary, as applicable. And they were more than willing to go extended into industrial IoT. So they're also trying to do microcontrollers, which run machine lathes. Everything on the industrial floor is what they're targeting on. So they're really into the tight loopback curve of control theory. And so their goal was actually how do I go create a Redfish service will run on as smallest object as I can. They started with a bunch of graduate students trying to implement this in machine code. That got to be a little laborious, so they up-leveled at least to Java because Java is pretty intense. They've released the Redfish model for industrial IoT. I've listed it, the title of it, and I've got the link at the very bottom. And so right now they've within the set of grad students, they will actually go generate this Redfish service framework in Java and auto-generate all the stubs. But they do it with the Redfish mockup and the OpenAPI schema, which is good that someone actually took that OpenAPI schema and is working with it. So all the behavior is static behavior is all auto-generated. That's mainly the behaviors of the get, probably a patch. And then special behaviors, of course, need to be coded just like in the Python emulator. It just provides you a framework, and you have to go implement. And so one thing he said when he released this was that he said, "John, I can release this, but it was written by two grad students, and they were on their way to something better." So I believe it builds. I believe it works, but we don't maintain it a whole lot. So if the industry is interested and wants to maintain it, they can do that. But the grad students themselves are actually just utilizing this for their particular purpose of driving it into industrial IoT. So the next implementation is C++ in C++. So back in 2019, Intel had this great initiative called RackScale. So RackScale was a design for a rack-level manageability of platforms. It pre-staged disaggregation and composition. And so RackScale basically said, we're going to decompose everything. We're going to have racks of memory, we're going to have racks of GPUs, we're going to have racks of storage, and we're going to have this composition interface, which allows you to compose servers, virtual servers, out of this entire disaggregated rack. And so they designed all this, and they actually made it all public. The code that ran on top of the nodes was called the pooled system management engine. So instead of the composition would be made out of these pools of systems, and each system would run a PSME. And this PSME would be run as a software agent, and so they wrote it in C to run on top of Linux, I believe. RackScale eventually was a little before its time, and so it got unfunded within Intel. And as part of that, Intel actually implemented three interfaces. It implemented the PSME interface, which was Redfish. It implemented the rack manager interface, which was also in Redfish, and then it implemented the RackScale interface, which was how do you go onto a RackScale, make a composition request, and have the entire system create a server for you and provide you the command line entry to get to its Unix or its Windows, whatever it had installed upon it. It actually open sourced all of it as part of the elimination of the program, and it was all kind of sitting out there in open source. So it came as a surprise, actually, when EdgeCore, which is a network company, said, we took the PSME and we modified it, and we actually implemented Device Manager on top of it. So what they implemented was they actually implemented PSME, runs on top of a switch OS, actually Open Network Linux, which OCP also owns. I have a diagram of this later. And so we've implemented, and we're going to donate it back to OCP. So OCP now has this implementation for its networking devices. Celestica, just last year, came in and said, you know, the edge core implementation was really nice, except it does not conform to OCP's baseline profile, which is the profile which every OCP platform is supposed to support. It says there's a couple of bugs in it, and it doesn't quite build right. So Celestica went in there and basically modified the code base to fix it all up, and then they released a product against it. So the way we use profiles in OCP is that in order to a product be OCP accepted or OCP inspired to get that moniker, OCP requires that it support the baseline interface. And so they were now able to submit a design specification for their particular switch and say that we are OCP compliant to the baseline by just adding this chunk of software. They didn't have to go add a BMC to the hardware. They just say, hey, we want to open network Linux from OCP. We can drop this software agent on top of that, and now we're compliant. Give us our moniker, and they got it. Okay, so the links at the bottom is basically the link to the rack manager and to the PSME, and the bottom is actually the switch that they were able to ship out. So this is architecture of the PSME Redfish service. So Open Network Linux is by OCP, and it's just a version of Linux that all the OCP networking folks deploy on the system. The API layer is just the interface layer for managing the OS itself. So PSME basically defines this, the actual PSME server. It's chassis agent, which is just the provider interface to talk to underlying hardware, and exposes the Redfish interface on top. So this PSME Redfish service supports the entire Redfish model. And in addition to that, they implemented the event service because Redfish is both a synchronous and an asynchronous interface, and it uses events to do asynchronous notification. And it does the various simple subscriptions for when you add a resource, when you remove a resource. So so the underlying chassis agent, as I explained, deals with the underlying Open Network Linux, and it sends its data to the PSME server. So it's a typical provider server agent interface. And so the bottom is actually what Open Network Linux, the API definition. So it just provides a logical abstraction to get to all the telemetry and capabilities which are within Open Network Linux. So you get to the fans, you can get the PSUs, you can get the LEDs. So at the same time that EdgeCore submitted to PSME, they said this was nice. This was a nice baseline. We could get to our baseline service, but we're dealing with networks, and networks have lots of switches, and we sell lots of them. So we've created this network, this device manager, which manages each switch and each node underneath that supports Redfish. So they contribute this as a bundle with PSME, and I have a diagram of how they interact together. But at the time, the build source was very problematic. So over the last 2 years, Intel has gone in and they've cleaned up the entire code base, and then they've added this Redfish interface. So the Redfish interface was actually being implemented by yet another group owned by the Linux Foundation called ODEM. So ODEM is a Linux Foundation project to create a fabric manager which manages across all telco. They're still working, but their interest is how do I manage from edge to central office? So they had a far more grander view of where Redfish could go. But what they did was they implemented a Redfish interface to interface with ODEM. So it gave a northbound interface, it implemented the aggregation model, it implemented from an update model, it implemented a whole bunch of models that Redfish had only recently created for them. So it was so I went to ODEM and I said, guys, I need a Redfish interface over here. Do you mind if we borrow this? And they said, we proudly give it to you. Just make sure you give us the right acclamation within the model that it came from us. And we said, we have no problem. This is all open source. It was all BSD. And so we've taken the year of actually re-architecting device managers. So we have an ODEM interface, and then the actual device manager code that we got from EdgeCore just became a provider, which for southbound Redfish. Because the way the aggregation model works is that it says northbound is Redfish, underneath can be anything. It could be IPMI, it could be Redfish, it could be SNMP, it could be one of many things. And the aggregation model basically says, I want to aggregate this device and provide a Redfish interface for it. And I'll talk to IPMI to it. Just tell me how I can do that, and I'll go ahead and do that. So this is how the initial contribution came in. So it had a northbound interface of just a command line interface. The device manager interacted with a Redfish service. That Redfish service could be within a BMC. It could be a Redfish service run on top of a NOS. So within a switch, EdgeCore had both a BMC and it had a NOS on it. And so it would actually, the device manager actually had two Redfish interfaces to a particular node, and it would actually integrate the telemetry it was getting from the system. They also had this vision that this Redfish service could run on other devices. It could run on a storage node if it needed to. And then at the very bottom is when it contributed to OCP. The OCP had this profile model where they had this hardware baseline profile which went across all OCP platforms. So the vision was that if you found an OCP platform, you knew the common manageability across the platform. You didn't have to ask it. It wasn't a, can you do this? It failed, okay, I can't do that. Maybe I can do something else. There were a fundamental set that you could find across all OCP platforms. And then if you were a server, there were particular things you could go off and do as a server that above the baseline. If you were a network device, you would have network ports and modules. If you were a storage device, you would have disk drives and whatever. SNIA has defined all that space. Hence, I've encouraged SNIA to contribute a profile to OCP, so we can start filling in these top-level boxes. Rack and Power is getting theirs. They've done an entire profile for liquid cooling within racks, and so we had a question earlier about abstraction layers. So the way we did liquid cooling was we within Redfish didn't do anything. We just went to OCP, Rack and Power, and we said, you guys are the SMEs. You guys know at what level of abstraction you want to go interact with the system. We as engineers would give you all the low-level detail, and they would say, we don't need the low-level detail. We need the high-level detail of this level of telemetry is what we need. We need to know when there's a leak. We need to know what we can do when there's a leak. And we will create this policy which says, if I discover a leak, then you will automatically shut the system down. And so we let the SMEs that do this on a day-to-day basis define the level of interface of abstraction that they want to deal with. Okay? Again, what we did with ODEM is that we took the, within OCP, we have a interface definition called OpenRMC, which is the interface on how you manage a rack. So at the rack level, you can go into the rack via OpenRMC, you can go up, you can reset the rack. So the device itself will decide how many systems it has, nodes it manages, and then it will reset each of the nodes within the rack itself. So what we did was we took ODEM, and it had the account service, it had the event service, it had task service, it had the session service, and it implemented aggregation model, which is group operations. So you want to be able within a rack to say, when I reset a rack, I may want to reset everything, but I may want to define an aggregate, some subset of a rack, which I want to actually do a reset to. And the aggregation model allows you to define that subset and then memorize that subset so you can go in and say, I want to reset all the compute devices, or I want to reset just the storage devices within the system. The same with firmware update. So you want to go into a system and you may want to update all the firmware in the system, or you may not. The aggregation model paired with the aggregation with the firmware update model says you can go into a system, go do a query on all the firmware in the system and say, well, all the systems that have firmware 1.3 and above, I won't touch, but all the systems within below 1.3, I want to go update. So you now create a subset via the aggregation model and say, do a firmware update across this subset of the rack. And so what we've done is we've added ODEM at the very top with all its services. We've deprecated, I guess, device manager, which only manages nodes supporting Redfish to just one of its providers. So in the future, this still allows us within the connection method allowed by the aggregation service that if there's the IPMI ODA system, we can still manage that. If it's a networking system that runs Netcom, we can go manage it using that. So only device manager has been connected up, and as other people decide that they want additional interfaces, you can go do that implementation. Okay. So the next steps for device manager, as I mentioned, device manager has this API, northbound rack management API. So next is it's got to conform to the source validator and the protocol validator within Redfish. So Redfish has its own conformance test suite. We want to make sure that this northbound interface conforms with it. And then we want to make sure that it now begins to support it begins to align with the implementation. So we had this northbound interface definition, we have this implementation, so now kind of askew because the implementation has to actually outrun the actual definition of the interface. And the goal here is the 1.1 WIP, which has actually been posted to actually support the update firmware at the rack level and to support reset system at the rack level. And so we use the implementation to propagate that down. The link that I have is the actual specification to what has been released, and then the sub-project within OCP to define this northbound interface for the rack. Okay. So in summary, the Redfish Swordfish community develops open source Redfish clients and libraries, which have been much more visible. So if you go and search, if you want to be a client to utilize this Redfish service or Swordfish service, they abound. We have GoFish for golang. So if you want to implement on the client side, they exist. But what we found is that the community has also developed a lot of Redfish and Swordfish service implementations. And they are just not as visible or as prevalent because a whole lot of people running around trying to implement this stuff, right? It's the vendors you go to and say, why don't you have a Redfish service in your system? That they say, well, various reasons. I can tell you now that they have implementations they can start from, which will give them a leg up in their implementation. And some of them support the entire Swordfish implementation. So as more management domains prescribe Redfish and Swordfish for their implementations, there's a larger impetus to get Redfish services into other management domains. That has driven Redfish service into IoT devices, microcontrollers. Another standards body that we're working with is the Open Group, which is OPAF, which is actually taking Redfish into process automation. So Exxon came to them 4 or 5 years ago and said, every 20 years, the process automation industry changes systems. And we want to go away from the vertical system, which we've been locked into a horizontal system, and we need a standard. So they've implemented, about 4 years ago, they defined the new generation of process automation to be Redfish. So they've gone, and they're heavily building software agents running on top of operating systems. And currently their stuff is proprietary, but there are, again, other implementations of the Redfish service. You just have to look for them sometimes. Okay? And with that, I think I am done. I'm 1 minute over. So do we have any questions? None? Okay, then I'm done. Thank you.